So we've just finished talking about measures of central tendency, and now we've got two sections where we're going to talk about measures of variation. In this section, we're going to talk about the variation we use when we have the mean. So remember, the mean is the center of data where we add all the values together and then divide by the number of items we have. Add each piece of data, divide by how many you have. That's the mean. We're going to see the what we're going to use is called the standard deviation. Deviation from the mean sort of tells us if whatever the middle is, right here, x bar, that we're going to get a standard deviation that kind of gives us how far, I'll just put SD, how far above, subtract the standard deviation, add the standard deviation, and gives us a sort of a measure of how spread out the data is. So we're going to talk about the standard deviation. And we will have two different standard deviations depending upon whether we're dealing with the population. With the population, we'll use this symbol, a sigma. It's not really good. Maybe that one, something like that. Greek letter sigma. And for the sample, we'll see one with the S, standard deviation. And the calculator usually goes S little x. And usually there's an X here saying that that's in reference to the data. So let's go ahead and get started. We'll take an example. Here is two different brands of paint. So a lab is testing this experimental brands of paint. They want to see how long they will last before fading. They're going to take 6 gallons of each paint to test. And for some reasons, different chemical agents were added to each group and only 6 cans are involved. They're going to call this two small populations. Okay, so everything we're dealing with a population, not just a sample. It seems like, oh, we're sampling out of it, but they made this up special, so they're calling this a population. So in your questions, make sure you understand and look for that whether you're dealing with a sample or a population, it will make a difference. And so we've got this. What we want to do is see, well, what's the average of these two different brands, and then what's the standard deviation. So we're going to, again, here's the mean for a population. We want the mean for brand A and for brand B. And then we're going to want its standard deviation, which we'll get from here. Standard deviation for A, standard deviation for B. And we're going to make a comparison there. We're going to do that with the calculator, and then we'll come back and see how the calculation works. Okay, so turn the calculator on and off, I guess. If we go to the home screen, just let me arrow down, arrow up. For statistics, we have these 4 menu items: statistics, regression, distribution, inference. Those are the ones we'll be using during this course. Today, we're looking specifically at the statistics one, and it's highlighted, so we're just going to hit OK. We have 3 things we can do with this. We can put in our data, we can graph it, and we can get the stats. We're going to go ahead and go to data, which is highlighted already, and we're ready to put in value 1 and frequency 1. So we put in 10, and execute will put it in. It automatically puts in a frequency of 1. If we had more of them, we could change that, but we're just putting in a list of data, so we're just going to enter the numbers this way: 50, execute, 30, execute, 40, execute, and then 20, execute. And at the same time, we're going to put in our data for 2. So value 2, frequency 2. Okay, so this will be brand B. We're going to put this data in: 35, 45, 30, 35, 40, and and 25. And I may have mentioned this before, but my dad was in data analysis and did a lot of different. He worked for NASA, well, at Boeing, down at NASA doing jet engines. So literally, he was a rocket scientist or an engineer. But he always taught me. He says, when you have data, garbage in, garbage out. So if you put the wrong values here, you're going to get the wrong values out. There's no way. So we've got to double check 45, 30. 35, 40. Make sure you put the numbers in right. This is my bad part. Okay. So I definitely have to check those. You may see in some of my videos, I missed something and I have to come back to it later, but try to do this. So what we're going to see is in red will be the values 1, in blue will be value 2. Okay. So what do we do next? Let's go ahead and we arrow up. And now we've got the data highlighted. We want to look at the stats. So we come over to stats and we're going to hit OK. They give us all this information. So the number of data points, 6. And you can see if you arrow to the right, you've got the values for, you got value 1 and value 2. They both have 6 pieces of data. Then there's a lot of other information. Most of this we'll be using later in the next one. But so we will keep arrowing down until we get to the mean. Okay, and I'm going to actually go on up. So this is the population mean. For 1, it is for brand A, it's 35, and for brand B, it's also 35. So we can go ahead and put that in there. It calculated the mean for us. And then you'll see right below it is a standard deviation. Notice the little symbol here is for population. It also gives us the variance. We'll talk about that in a moment. Then it also gives us the values for the sample. Sample mean, if this was a sample, we could have the sample mean and sample standard deviation. Notice there is a difference between the sample standard deviation, it's 18.71, versus the population standard deviation, which is 17.08 rounded up. We're going to put that for brand A, 17.08 rounded up. Okay, and then for brand B, we go over and its standard deviation of the population is 6.45. Yeah, rounded 6.45. And notice if this was a sample, that standard deviation is down here. That would have been 7.07. So again, you have to know whether you're dealing with a population or a sample. It's crucial. If you get it mixed up, again, you'll be close, but you won't be correct. And we're going to see why that is when we get to the calculation part. So what does this all mean? Well, it means for brand A, on average, the mean, the paint lasts for about 35 months. That's the average. But the data is spread out. You could get 17.08 more months on average, a standard deviation, 1 standard deviation. So if you add 17.08, you would get to, let's see, that's 12, carry the 1s, 40, 50, 52.08. And if you were to subtract 17.08, subtract it, you would get down here, which is going to be 35, 25, 15, not quite 20, come back 3 more, 18. I think it's, is it, well, let's just do it right real quick. So we can always come back to our calculator. And 35 minus 17.08. And like 17.92. Okay, that's what I was thinking. We were about 17.92. Brand B, on the other hand, it also has an average of 35 months before fading, but what's happening is the average spread is an additional 6.45. So that's going to give you 41.45 or subtract off 6.45, and that gives us 28.55. Okay, so an above and below. That's what the standard deviation tells us. It tells us if you buy brand A, you will average 35 months, but you may do very much better, right? On average, an average deviation, you could get up to 52 months or further, or you could do much worse at 17, about 18 months. Whereas if you take brand B, you can expect that you're going to get the 35 months and the spread is less. You're going to get closer to that. You might get the 41 months, but you also, if on the other side, on average, be down about 28 months. So we have more consistency. This is more consistent. This is more variation. Less consistent. More consistent. Less variation. And again, it's not whether it's a good or bad thing. Brand A's variation, somebody got 60 months out of this. That's pretty good. Brand B, the highest they got was 45. But again, you get this, if you're looking for like a consumer product, typically companies like to be able to say something and when you buy it, you want to be able to get it. With brand A, someone only got 10 months out of it. There's a very unhappy camper, as we say. Okay, so that's what standard deviation gives us, and we're kind of going to move through now and see what the calculations look like. So how is this calculation done? And what we're moving here is to try to understand the calculations. And just like, so we always start with what is the mean. So we would add these all together and divide by 6. And again, if you do that, let's see, here's 6 and 4, that's 100. There's 50 plus, so that's 210. 210 divided by 6 gives us 35, an average. So what we do to calculate the standard deviation is we take each data value and we subtract the mean. So in this case, we get negative 25, 60 minus 35. This one we get positive 25, 50 minus 35, we get positive 15, 30 minus 35, we get negative 5, 40 minus 35, we get positive 5, and 20 minus 35, we end up with negative 15. Now, so those are the deviations from the mean. That's where that word deviation comes in. These are the deviations. If we wanted to try to get an average deviation, we could add these together and then divide by 6, right? But the problem we run into is you'll see a negative 25 plus 25, that's 0. Positive 15 minus 15, that's 0. Negative 5 plus 5, that's 0. Which if you add all these together, you get 0, and you will always get 0. That makes this whole process sort of worthless. So we're at a dead end. We cannot get we cannot get an average deviation this way. So somebody got the idea, well, let's see if we can do some mathematical manipulations. So one idea that has stuck is let's square each of these deviations, because if you square each one, they will all become positive. Then when you add them together, you will get a number and then get the average of that, and let's see how we do. So we're going to take, let's move to the next step. We're going to take negative 25 and we're going to square it. That gives us 625. We're going to take positive 25 and square it, and we'll get 625. We're going to take 15 and square it, and that gives us 225. We're going to take -5 and square it, and that gives us 25, positive 25. Positive 5, square it, that gives us 220, or just 2, gives us 25. And finally, -15, we're going to square that, and that gives us 225. We are going to add all these together. 625 plus 625 plus 225 plus 25 plus 25 plus 225. And we get 1750. 1750. Now to get the average, there were 6 of these. We are going to divide by 6. Okay, and so we will divide, and notice how it brings back the answer. I just hit divide. Divide by 6, and that gives us about 291.6666. That's what we call the variance, and it's our sigma squared, because remember, we squared it. Now, there are some things in statistics where we might use this variance in more advanced stuff. In my use of statistics, it has just been a halfway place to calculate the standard deviation, because what did we do? We did a manipulation. We squared this. So how do we unsquare things? We use the square root. So we're going to take the square root now of 291.67, and over on the calculator, notice I've got a button to bring back my answer. Here's the square root, and so I just hit the square root button, say put the answer in there so that I have all this rounding going on, and I hit execute. 17.08 if I round it. That's exactly the figure that the calculator gave us. So that's what it's doing. Okay, so that's the process. Again, if we had more data, which we will, it's going to be very tedious to do this type of calculation. So that's why we've got the calculating devices. That's why statistics is done with calculation packages. Okay, we could do it for B, but again, if you'd like to, there it is. Practice it. Just kind of see how it works. I just want you to be able to see that what we're getting is how far from on average, what the standard deviation gives us is on average how far from the mean are we. Okay, so we use it for a comparison between two different sets of data, say like for brand A and brand B of the paint. However, why is there a difference between the standard deviation for the population and the standard deviation for the sample? We'll get there next. So a picture here, this is what a graph of a variation looks like. And I'm going to go back here to our calculator, and I'll show you. Let's see, go back to the menu. We're going to go back to statistics. We're now going to go over to the graph. Graph for these, whenever we're using the mean and the standard deviation, the best graph to use, we could use other ones, but what we're going to use is a histogram. And I'm going to hit execute to go for graph. We have these choices, so let's choose histogram. And notice it sort of automatically sets up frequencies. So see, here's one. So it, you could do, like, I guess it gave us a bar graph up there. This is what the histogram would look like for V1. Notice very spread out, one of each. And here's what it looks like for V2. Notice there was 2 of the same value there. In the middle, less spread out. So we can see that the histograms are a little different. Now you can go to settings, and you can select your bin width starting at 10. You can make it wider. I don't know, let's make it 10. See what, it'll give us a different look. Play with these things, and so now if we make it 10, now they're all touching like we were expecting, but then that only gives us 3 bins down here. But we can do this comparing brand A to brand B with graphs. Okay, and if we do that over here, this is some different data. It says starting salary at these corporations. They both seem to have about the same mean, maybe right here about this, but this actually might be skewed one way or the other. If we look at this as sort of the middle, we can see around this point, Corporation B has more variation, which again is a good thing if you're on the higher end, maybe making a little bit higher money, but it also means you might be at the lower end and making less, right? There's no one over here. Corporation A's starting salaries are all tightly packed around the mean, so less variation. More consistency, right? Corporation B has more variation. So the standard deviation is going to be bigger here, the number, and the standard deviation over here is going to be smaller. That's all we can say. And again, you can almost measure it here to say 53 to maybe about 60. So that's what? That's about 6.5 if you went 6.5 that way. So maybe a standard deviation of about 6.5. This one, you're going to see a standard deviation closer to going up there and down there, maybe about 22. About 22. And I'm just eyeballing it. Okay. So here are some things. The standard deviation measures the variation of the data set in relation to the mean, how far above and how far below. A standard deviation of 0 means that all of them would have the same value. You cannot have a negative standard deviation. And we just sort of talked about that the farther from the mean, the value of the standard deviation increases. So the more spread out, the bigger the value of the standard deviation. Now here's the reason why a sample has a different number. For the population variation, we did this. We got the deviations, we squared them, we added them together, and we divided by the number of pieces of data that we had. To get the standard deviation, we then took the square root, which gets us back to where sort of, an average deviation from the mean using this value of all the data. When we go to the sample, remember our goal with statistics is that the sample somehow is representative of the population. Because there is some error in the sample, what they have determined is that to address the error of sampling, we can instead divide by 1 less than all the number. So and over here in the paint, we divided by 6. Had it been a sample, so we would have 1750. Had it been a sample, we would have taken that 1750 of sample of A, and we would have divided by 6 minus 1, which is 5. So we would have divided by a smaller number, which ends up giving us a bigger result, and that's why the sample standard deviation is always a little bit bigger. And again, once we get the sample variance, we turn that into a sample standard deviation by taking the square root. The calculator will handle all of this for us. We just need to know that that's what's going on here. This is an attempt to make the sample more representative of the population by dividing by 1 less. And what you'll see is that when we get to about 30, we get to about the same place. So let's take a look at that. Here is some data with actually 30 pieces of data. So we're going just to do this, and we'll see how the technology can really help us do this fairly quickly. So we come back up here to the data. I'm going to go OK. I'm going to leave this data. Maybe we want to use it again. We've got a value 3 here we could use. So let's just put this data in, 42, 14. And what I'm doing is I'm going to go across and keep going. And what it's doing is it's putting in a frequency of 1, which is what I want for now. Oops. What did I do there? I did something, 46. Okay. And I made an error over here. It's not 46 frequencies, just one. Okay, let's get back on track. 30, 23. If you want to fast forward through this, you could, but just again, you just need to be careful to enter all your data correctly. But you'll see we could do this relatively quickly. If we were to calculate this by hand, it would take me maybe 10 times as long, right? And it would be much more easy to make a mistake doing all this calculation by hand. And even 23, okay, then 72, and then 35, 34, 30, 60, 30, 64, 14, 36, 23, 42, 35, and finally 72. I see I made a mistake up here. I put in 64 and 14 on the same line, so I'm going to come back up here and fix that. 64, and then I'll just put the 14 down at the end. They don't have to be put in order. It will all take care of that for us. Okay, but we put it all in. I'm going to go up to stats. Just hold it down. And I'm going to hit OK. Remember, I'll have to go over, so it's not, we don't want all this stuff. We want the mean and the standard deviation. And in this case, we are told that it is a sample standard deviation. So let's see. Let's compare this. Mean for the population, mean for the sample, and we have to arrow over 3. So 37.1, that's the mean. And notice the difference between the standard deviations. For the sample down here, the S, it's 15.48. So we'd want to put in 15.48. For the population, it would have been 15.22. So they become closer and closer. And again, if you had like 50 pieces of data, these two numbers become closer and closer because the difference is you're just dividing by one less, and it becomes less of a consideration the more data you get. Okay, so we can do that fairly quickly. And again, if we want to look at the graphs, we could come back, come here, and now we've got 3 graphs. You can also get rid of some of this data if you want, and you just sort of see. But again, you start to see it's different data, right? But a way to comparison. And it wouldn't make sense to compare the first 2 data, which is the paint, to this, which is office rental rates. But you can see the values there. Okay. So let's keep moving. We look at these drawings. Remember, if the standard deviation is 0, that means that all the values are the same amounts. So here's one with the standard deviation of 0. Everything is 5. All 3 of these have a mean of 5, right? The average is 5. But watch how the data looks different depending upon what the standard deviation is. Here we're at 5, but on average 1.2 above to 1.2 below. Here we're at 5 is our, but there's actually no data here, but the standard deviation is about 3 above to 3 below is kind of a, most of the data. Okay, now we're going to look at histograms, sort of if we have a frequency chart, a frequency graph, histogram, that is bell-shaped. So it's got a special characteristic because it is symmetric, it's a bell-shaped. What we find out that if we get the mean and the standard deviation, and we'll see a picture of this in a moment, that if we go 1 standard deviation above and below, so here's our mean, 1 standard deviation one below, one above, that we will encompass about 68% of our data. This is an empirical rule, which means it's just observed. It happens because this is what nature does for us in a bell-shaped distribution. Things that are bell-shaped distribution typically come from things that are sort of random, have a randomness to them, very complicated. Things like genetics are typically follow these empirical rules. Things in nature a lot of times. If we're going to 2 standard deviations, that's about 95% of the data. And then 3 standard deviations, we end up picking up 99.7% of the data. So what does that look like? Here's our drawing. Here's our mean. And again, they're using a sample mean, but could be a population mean, right? If we go 1 standard deviation above to 1 standard deviation below, that encompasses 68% of the data will be there. And since it's symmetric, half will be below, half will be above. So we could use this number, and we're going to do an example of how we could use that. From 2 standard deviations, 2 above to 2 below, that totals 95. And again, because it's symmetric, half of this, 95 divided by 2, would give you 47.5. So you could calculate, okay, 34 minus 47.5 minus the 34 gives us the 13.5 for just this little region between here. Okay, so you could use that. I would, it's to me more difficult to kind of remember these numbers. I would go with just the half numbers. And finally, the last one, if we go out 3 standard deviations, we will get 99.7% of our occurrences will be there. Okay, and we'll take a look at this. And again, you could take 99.7 divided by 2, subtract off the 47, and you get this little part between 2 standard deviations below to 3 below. Only about 2.35% of the data is there. That's what happens when you have a bell shape. Okay, so a way we could use this is using the empirical rule. We have a survey that's been conducted. They give us a sample mean height of women in the United States was, so this is a mean, 64.1 inches, about 5'4.1, with a sample standard deviation. So there's our standard deviation of 2.6 inches. We're asked to estimate the percent of the women whose heights are between 58.9 and 64.1. So one of the ways we can do this is we could just kind of draw our chart. Let's label the mean 64.1. Having the standard deviation, we can go above and below. Let's look what they want. They want from 58.9 to 64.1. Well, where's 58.9? Here's 64. 58 is going to be somewhere below that. And then we're going between, 64.1, that's the mean. So we want to know what percent would be in this portion of the graph. And again, we have our bell shape, which is important, right? We need to find out how many standard deviations this is. And if so, we could take 2.6, we could subtract that once. And that will give us about 62, 61. Let's just come back here. 64.1. It's easier to add than it is to subtract for me. So 2.6, because I might mess it up, 61.5. So 1 standard deviation would have been 61.5. Let's subtract the standard deviation again. So minus 2.6, and we're at 58.9. So 58.9 was 2 standard deviations below. 2 standard deviations. I just like to use SD as my abbreviation. It's harder for me to make those Greek letters. And it's below. Remember, if we're 2 below to 2 above, two standard deviations above, that would be 95%. But we only want the lower part. We only want half of that. And so this would give us the 47.5% of the women would be between 58.9 and 64.1. So we're using that empirical rule to do that. Here's a picture that they came up with. They're using more exact values, but who's going to remember those? Again, the empirical rule, 47.1. So you could add those together, but I would just take, well, that's going to be 95% from 2 below to 2 above, remembering that's what the empirical rule is, and then we would divide that by 2. Okay. And finally, we've got another rule that came up, Chebyshev's theorem. And yeah, some of these just, people are doing math and they're trying to find these. This will work with any data set. So these are not necessarily symmetric, although this rule will also work for symmetric. We'll see that if it's k standard deviations from the mean, this proportion is there. So how do we do that? If k is 2, so that would be, here's our mean, 2 above to 2 below, standard deviations. It says that regardless of what the distribution looks like, whether it's bell-shaped or not bell-shaped or skewed, whichever, that there will be at least 1 minus 1 over 2 squared, right? That's using this formula here, which equals to be 1/4, 1 minus 1/4. Get a common denominator, that's 4 over 4 minus 1/4, right? So that's how they got the 3/4. That's 75%. 3 divided by 4 is 0.75. 75% of the data lie within 2 standard deviations of the mean. If you want 3, 1 over 3 squared is 9, so you get 8/9. So we get 88.9. Now that is in keeping with the symmetric one, right? This is at least 75%. The symmetric one, actually, if we have the bell-shaped curve, that would have given us 95%, which is more than the 75%, but that's okay. This says at least. And the same thing for 3 standard deviations. It's the symmetric one, remember, the empirical rule was 99.7%, which is more than the 88.9. So how do we use this? Here's a sample problem. So here, from a sample of 16 in equal set, the mean number of pets at a household is 2. So that's our mean. We'll put that's the middle, is 2, with a standard deviation of 1 pet. So here's 3 pets, that's 1 standard deviation. Here's 1 pet, that's a standard deviation below. If we go 2 standard deviations, that would be 4 and 0. And we can't really go 3 further below, right? But because you can't go negative. Using Chebyshev's theorem, determine at least how many of the households have 0 to 4. So 0 to 4, what we're seeing is, again, the 2 is our mean. So this is 2 standard deviations above to 2 below. That means k is 2. This is 2 standard deviations. We've already got the calculation, so we could, we would go through these same steps, but you'll get that it has to have at least 75%. That's Chebyshev's rule. We don't need to know that this is bell-shaped. Now, if they told us it was symmetric, we would have said, symmetric, it's bell-shaped. Then we would say, okay, we could use the empirical rule on that kind of data. It would be 95. But not knowing anything about the distribution itself, not knowing whether it's symmetric or not symmetric, the best we can say is it will have at least 75%. Okay, at least means more, 75% or more, and that's that. And then we'll get into section 2.5 next. Thanks.